In this video, we will learn how to apply the central limit theorem to sample proportion. The control department of a light bulb manufacturer randomly picks 4,400 light bulbs from the production lot every week. The records show that when there is no malfunction, the defect rate in the manufacturing process due to imperfections in the material used is 1%. When 1.5% or more of the light bulbs in the sample of 4,400 are defective, the control unit calls repair technicians for service. First of all, let's see what kind of information we can extract from everything we've read so far. So I know that the sample size is 4,400. That's how many light bulbs are inspected. And I know that the proportion of those light bulbs that are defective will be 1% or 1/100th. To be able to use the central limit theorem, we need to make sure that a couple of assumptions are met. We need to check that the product of NP is at least 10 or more. So when I multiply the sample size times P, I get 44. And when I multiply the sample size of 4,400 times the remaining 1 minus P, which is really 0.99, I get 4,356. Both of these numbers produce at least 10, which allows me to use the central limit theorem. The central limit theorem says that even if your population is not normally distributed, when you take samples long enough, the proportions P hat that you're going to get as a result, those will be normally distributed. In addition, the central limit theorem states that the mean of those sample proportions will be equal to the proportion of the population, and standard deviation of those sample proportions will be equal to square root of P times 1 minus P divided by sample size n. Recall that the central limit theorem states even if your population is not normally distributed, the sample proportions will be, and therefore I can use the normal CDF to find the probability in question. The probability that P hat will be greater than or equal to 15 thousandths is equal to normal CDF, starting with 15 thousandths going to the right infinitely far, with the mean of the sample proportions of 1/100th and standard deviation of sample proportions of 15 10,000ths. That results in 4.2912 times 10 to the negative fourth power, which is the scientific notation of a very small number. We need to move decimal point 4 times to the left in this number. Moving decimal point and of course taking into consideration the directions on rounding, I end up with 0.0004 or 4 10,000ths. Therefore, the probability that there will be more than 1.5% of light bulbs in the sample of 4,400 of them defective is very small, which is great for the manufacturer. Here is one more example. Empirical research on stock market data for 2 consecutive trading days indicates that 60% of the stocks that went up on the first day also went up on the second day. Yesterday, 600 stocks went up. What do I know? I know that proportion in the population is 60% or 60/100th. The sample size is 600 because we are considering 600 stocks that went up yesterday. According to the central limit theorem, we must satisfy 2 conditions, and they are the following. Product NP and N times 1 minus P must be at least 10 or more, which I check and I'm definitely in the clear. Therefore, I now need to compute the mean of sample proportions and standard deviation of sample proportions. The mean of sample proportion will be same as the population proportion, which is 60/100th, and standard deviation of sample proportion is equal to square root of P times 1 minus P, in our case 60/100th times 40/100th, that divided by the sample size of 600. This square root produces the result of 2/100. Now I'm ready to apply the central limit theorem and compute the probability that p hat is less than 0.59, which is normal CDF, from negative infinity to 0.59 with mean of 60/100 and standard deviation of 2/100. This results in 0.3085, and I had to round to 4 decimal places based on these directions.